Hello everyone, welcome to Vibrations and Acoustics. This time we're going to do an example based on a beam with a weight hanging off the end of it. And we basically want to find the equivalent spring constant of this system so that we can later on put it into an actual equation and figure out what the vibrational characteristics are. So, we're going to go ahead and jump right into this. The first thing we want to do is basically establish what kind of a system this is. So, what you can look at right here is say, well, the beam's going to bend down like this, like a spring, and then the rod's going to stretch slightly based on how much the weight is. So you can basically think of it as a vertical system where you have one spring, the beam, directly connected to another spring, the rod, with the weight hanging right off the end of it, just like this. Because the beam spring constant is a relation that is based on how far it's bending, so you could model it just like this. It might be a little bit of a stretch to go from horizontal to vertical like this, but since the weight is moving vertically, that's basically the plane that you want to look at. You want to look at the whole system in a vertical manner. If this was a joint up here, then it might change a little bit because you'd have a rotational system going on, but that's a different problem that we'll handle at a different time. So, since we have the beam and the rod, we're going to call this KB and KR. So for a beam that is in bending like it is right here, the spring constant for it is equal to 3EI, so the moment of inertia right there, all over the length of it cubed, and I'll put a B down here just to make it even clearer here. For the rod, K of a rod stretching, its spring constant is E over the times the area over L, R, the length of the rod. And all of these values are given, or you can calculate them. E is a material property, so you should be given that in order to solve this problem. A is something you can get from the diameter, and length is something that should be given again also. Okay, so now we have two springs in series. Now springs in series, springs are very similar to circuits if you've ever had resistors, but they're actually the inverse of resistors. In circuits, resistors that are in series like this add together resistance. But springs, when they are in series, have the relationship of KB, KR, all over KB plus KR. So springs in series act like resistors in parallel, basically. So it's an inverse reciprocal relationship there. So this is the relationship for springs in series. If you're doing springs in parallel, this is series. If it happened to be in parallel, then it would be equal to KB plus KR. So really easy there. But this problem is a little bit more complicated than that. So another way to look at this, if you were to take the inverse of this and make it 1 over KEQ, we're going to do this because it's going to be slightly easier, and then sub in these values. Hang on here, let me check something. Yes, 1 over LB. We've got 1 over KB plus 1 over KR. I was going to skip this, but I think I should show it to you right now. Which is going to be equal to then L cubed B all over 3EB IB plus LR all over ER. So, which is equal to 1 over KEQ. If you had numbers, this would be a good time to substitute those in, but since we don't, we're just going to go ahead and find a common denominator and just solve this all out symbolically. AR, LB cubed plus 3 EB IB, can you see that? LR, all of this over the common denominator of 3 EB IB ER AR. So what I just did was multiply these across, create a common denominator, added it together there. You can then take the inverse of this because this is 1 over KEQ, and then KEQ is going to equal 3 EB IB ER AR all over are AR LB cubed plus yada yada yada. It's that notion right there. So that's your K equivalent. So basically the main thing to take away from this is when you have a beam that's bending, you got to be really careful how you set up the system here. This can't be in parallel because since they are directly connected, they can move independently of each other. This can stretch a little bit without really pulling this down any further, and this can stretch a little bit without really lowering that at all, or affecting how far this spring stretches. They're independent. Okay, but you have to do it vertically because the weight's moving up and down vertically. Springs in series are this relationship right here, and you can add on more, multiply another K right there and add another K down here if you have 3 springs. And then parallel, you just add them straight up. And then this is a relationship. If you don't want to substitute directly into that relationship and then simplify it, it would have been hard because we have these fractional values for K, each one of the Ks. So it would have been just as difficult to simplify this equation. So we started like this, gives us an inverse, and then go ahead and solve it out. It's basically an algebra problem. That's how you find the equivalent spring constant for a beam. There's also these equations which you ought to note, which are beam bending and basically wire stretching.